All right, my fabulous chemistry students, video number 3, heating and cooling curves. Now we're going to take all that information we learned from last video, those vocabulary terms, now we're going to apply them to how do we actually write these things on paper. And it's going to be a little bit involved, I promise, right? Heating water, is not all that difficult, right? So why are we even dealing with this? Well, we're going to find that as we change phases, there's different kind of energies going on, and that's what we really need to be able to depict. Okay, so here is a particularly that says heating and cooling curves. As you see here, the temperature is going up. So right off the bat, when I see that it's higher on the right-hand side, this is a heating curve specifically. Okay, and we have to be able to label all of these things. So let's get right into solid, liquid, and gas. Solid, we're going to use a little S, right? In liquid, we're going to use a little L, preferably cursive style. In gas, little G. And now what's going on here is when I level out here in section B, I am going from solid to liquid, changing phase. And in C, I'm just one phase, I'm liquid. And then here in D, I'm going from liquid to gas. We should be able to label that, right? As I go from solid to liquid, right? That's what we call melting. Or that new fancy word we had, fusion. And as I go from liquid to gas, the big bad word here is vaporization. Or sometimes we can refer to that as boiling. Okay? So these are our different phases on the graph. But now let's add energy wrinkle into it. So kinetic energy, and you might want to color code this to some degree. I'm going to color code it. If you have two different colors, now would be a great time to use them. Kinetic energy. Kinetic energy, remember, is the measure of kinetic energy is temperature. Remember, so they're very, very closely related. So where my temperature is changing, I will have a change in kinetic energy. And that just so happens to be on these slant lines. And if you can see, because I have temperature over here or kinetic energy on the left, there is a change in temperature here. Therefore, there has to be a change in kinetic energy. That's really one of the biggest keys to this whole part and one of the major topics of this whole unit. As temperature increases, kinetic energy increases. As kinetic energy decreases, temperature decreases. And I just said that backwards, but same thing. Kinetic energy is linked with temperature. Now, potential energy isn't. Potential energy, we're going to find, is where the change in phase is happening. That's going to be this flat line. And so both flat lines is where the potential energy is increasing and the kinetic energy is staying constant. So let's just think about this real quick. I'm going to have a sauce pot. I put it on the stove. I put some ice cubes in there, and I turn it on. Well, we know I'm going to add heat because the stove's adding heat to the pan, and that heat is going into the ice, and the ice is slowly going to melt and turn into liquid. Well, at this point B here, is the temperature changing anymore? Do you see a change in temperature? But isn't the stove still on? And I'm adding heat, right? But the temperature is not changing. Because what's happening is the energy is now going from kinetic energy into what we call the phase change, which is the potential energy. So phase changes are linked with potential energy. And isn't that cool? Potential starts with P, and so does phase. So the phase change is the potential energy, okay? And then we're going to keep heating it up. And we're actually going to do a lab on cooling curves, which will be next. And you'll see, you guys are going to be able to actually get to see a spot where the temperature stays constant. And that's good. So now, section A, B, C, and D, as they apply to the graph on the top of the page, right? At A, there's one phase, it's solid. At B, there's two phases, solid, liquid. At C, there's one phase, liquid. Two phases, liquid, gas. And at E, there's one phase, gas. So is at A, there a change in temperature? Yes, there is. And at B, it's flat, so there isn't. And C, yes, there's a change in temperature. And D, no, there isn't. And an E, yes, there is. And we should know there's a link here because temperature is the measure of kinetic energy. So in a graph like this, they're going to be very much linked. And you'll see our answers are actually going to be exactly the same because when our kinetic energy is changing, in this case increasing, so will our kinetic energy be. Okay? Then if our kinetic energy is increasing, the temperature is going up, we will find no change in potential energy. That happens when the temperature stays the same. That is when the potential energy is going to increase. That will be our phase change here. I'm going to use the delta sign. And also remember, this kinetic energy changes, the line is going to be slanted. When potential energy is increasing, the line will be flat. That's the two key pieces you need to know about how we use these graphs and to take away from this moving forward. Now there's two things different on this graph. First of all, number one, it is a cooling curve, and then it's actually depicted a little bit differently. The points have our letters. So this is going to be segment AB and not just A anymore. So let's go ahead and label this thing right up. We're going to start with gas up top. Then I'm going to have liquid in the middle. And then as we cool, we're going to form into a solid. Okay? In between, I have gas going to liquid. And we call that condensation. And for this phase change from D to E, we have liquid going to solid. And we call that freezing or solidification. Okay? And what we're going to be able to do now is be able to pick out from these graphs, oh, well, now if I can do these with the phases, then I could say, oh, this is the freezing point. So let's go to the next page and start manipulating these things. We'll fill in this chart first. Right, one phase for gas, one phase for liquid, one phase for solid, and its subsequent sections A, B, C, D, and E, F. Two phases at B, C, and D, E. That is where our phase change is happening. We will see in section AB we're decreasing in temperature, correct? It's got a slant. Again, temperature and kinetic energy are very much linked. So where I'm going to have a decrease in temperature, I will have a decrease in kinetic energy. Where the temperature is not changing, the kinetic energy will not be changing. Okay, and then in this case, it's actually the opposite again for potential energy. If the temperature is decreasing, the potential energy stays constant. When that temperature stops changing, that's when the potential energy decreases. This is where our phase change happens. And again, that happens at the flat lines. Kinetic energy will be at the slope lines. This one, it's a cooling curve, so it is sloped differently. Phase changes. And now throw in some energy. So as energy increases, that's going to be linked to certain phase changes. So all these up arrows are going to be linked. So if I go from solid to gas, we call that sublimation. Right? And if I go from solid to liquid, we call that melting. And our new word is fusion. Okay? And from liquid to gas, we call that vaporization or boiling. And then when energy decreases, I'll do this in blue. If I go from gas to solid, the opposite of sublimation is deposition. Probably want to put a star next to this one. This is going to be the hardest one to remember. Gas to liquid, condensation. Not a lot of room, I know. Liquid to solid, I'm going to call that freezing or solidification. And now we can see that certain phase changes are going to be associated with an increase in energy, and certain ones are going to be associated with a decrease in energy. And it's going to seem a little confusing at first, but I promise, as long as we start keeping in our mind what heat really is, it'll all start to kind of make sense. So two very new vocabulary words. We have endothermic and we have exothermic. Endothermic, we're going to absorb heat. Exothermic gives off heat. So exit. Exothermic, heat is exiting the system. Okay, and here's a heating curve. First of all, we see it going from low to high, so it's a heating curve. It says, at what temperature will the substance boil? Well, let's go in and start just labeling up our phases first, so that's going to help us. So I'm always going to start at a solid, then I'm going to turn into a liquid, and then a gas. And then in between, I have solid to liquid, and then liquid to gas. Okay, so now it says, what temperature does a substance boil? Boiling is going from liquid to gas, so that's here. If I follow the dotted line over, I see 90 degrees. At what temperature will this substance become a liquid? Now, this question isn't so good because if I was cooling, I'd become a liquid at a different place. But because it's a heating curve, we're going to go from solid to liquid. So here is where I'm going to turn into a liquid, and that would be 55 degrees Celsius. So a lot of things from this chart we can get. It says between 55 and 90 degrees, the kinetic energy of the substance is. So between 55 here and 90 here, what's going on with my kinetic energy? This line right there. It is increasing. Kinetic energy is increasing because there's a change in temperature. And then it says at 90 degrees, the potential energy of the substance is. So let's find 90 degrees. Come on over. Oh, is my kinetic energy changing any? No, it's at the same temperature. So if the kinetic energy is staying the same, it's the potential energy that must be increasing because I'm still adding heat, right? So that heat goes into what we call the phase change. So the potential energy is increasing. Of course, now I just asked those questions in the forward direction. I could ask the opposite questions to the same pieces and expect the opposite answers. And you know it's going to happen at some point, right? Once we get really good at these, I'm going to start asking these questions backwards. So let's look a little bit farther into exothermic and endothermic. Exothermic is the release or give off, right? Heat is leaving the system. To us, this will feel hot, usually. Except, of course, when there's a phase change. That's a little bit different. Freezing and condensation are where the phase changes where this is going to happen. And I know it, you say, Mr. Milks, it's freezing. How is that going to feel hot to me? But let's just think. In order to go from freezing, that is from a solid, I'm sorry, that's from a liquid to a solid. Oopsies. I'm going to go from a liquid to a solid. In order to do that, energy must leave the system. So energy leaves. Energy exits the system. Same with condensation when I go from a gas to a solid. All right. The non-examples would be all endothermic reactions. Okay. Definition of endothermic. System absorbs or gains heat. To you, this should feel cool or cold, especially if there's not a phase change going on. When there's a phase change, that's going to be melting and boiling. So melting is going from solid to liquid. In order to do that, I have to add heat. So think about it that way. And boiling is going to go from liquid to gas. In order to do that, again, I must add heat. Non-examples will be all exothermic reactions. And whew, we've reached the end. There's a lot to take in there. You might have to watch this video more than once. I promise you this is one of the top 3 things in the unit that we must master: potential energy, kinetic energy, and how they relate to our phase changes. In practice packet 3, page 3.1, practice packet 3, I said. In page 3.1, there's a curve that you get to create on your own based on the information you get. It'll be good practice. When you're done with that, there's a quiz called Energy and Phase Change that will relate to this homework in particular, and you will be well on your way. See you guys tomorrow in school.